Hello all. In this lecture, we will discuss the canonical form of elliptic equations, second order elliptic equations. Okay. Uh, we have already found the canonical forms of hyperbolic equations and parabolic equations. But when compared to the calculation of or transformation of these equations into the canonical form, means that means we are finding a non-trivial transformation, non-singular transformation theta and eta, in which the equation has a simpler form. That is actually the canonical form. But when we move to finding the canonical form of elliptic equations, the thing is not so easy as they compare to hyperbolic or parabolic case. But when we assume that, so one more thing is needed for finding this elliptic case or solving this elliptic case. That means when we assume that the coefficients of the principal part, we know that the type of an equation is determined by the principal part, that is by the discriminant, which is given by the principal part of the second order PDE. So when we assume that the coefficients of the principal part of the equation are real analytic functions, if the coefficients of the principal part are real analytic functions, then the procedure for finding this canonical form of elliptic equations will become something more easier and when and can be found or determined as in the case of hyperbolic equations. So first of all, what we have to define what are real analytic functions. Okay. Um, so we move to the definition. Let D be a planar domain. A function f from the domain D to real number R is said to be a real analytic in D if for each point x0, y0 in D we have a convergent power series expansion. F of xy has a convergent power series expansion in some neighborhood of that point x0, y0. So for each and every point, each point in the domain D of the function f, it must have a convergent power series expansion in some neighborhood of that point. Okay, if such a convergent power series expansion exists for f, then we can say that f from D to R is a real analytic function in the domain. So the power series expansion is f of xy is equal to summation k varies from 0 to infinity and j varies from 0 to k. It is we know it is a function of x and y, isn't it? So, the coefficient aj k minus j into x minus x naught raised to j, y minus y naught raised to k minus j. It is valid for in some neighborhood n of x naught y naught. Then in that case we can say that this function is real analytic. So when the coefficients of the principal part of the second order elliptic equation is real analytic functions, then the method will be, we can find the canonical form of elliptic equation as in the case of hyperbolic equations. Okay. Now we move to the theorem which says about the existence of such a canonical form for elliptic equations. Suppose the second order PDE, the given second order PDE LU equal to A UXX plus 2B UXY plus E UYY plus D UX plus E UY plus FU equal to G. The equation number 1 is elliptic. Elliptic in a planar domain D. Assume further that the coefficients are real analytic functions in D. Then there exists, the theorem says that then there exists a coordinate system theta eta in which the equation has the canonical form. Which is the canonical form? Canonical form is W theta theta plus W eta eta plus L1 of W is equal to G of theta eta. So this is the canonical form of elliptic PDE. Coefficients of the second order terms W zeta, zeta and W eta, eta are 1, and it contains only the remaining part is only the first order differential terms operator, and the right side is a function of zeta and eta which depends on the given equation. Okay, so the term second order term W zeta eta is absent in this transformed equation. So we need to prove that there exists a coordinate system, such a coordinate system zeta and eta, in which the given equation 1 has a simpler form W zeta zeta plus W eta eta plus L1 of W is equal to G of zeta eta. Okay, so let's move to the proof. As the equation is should be in the second order, we assume without loss of generality that one of the second order coefficients, that is small a, b, or c, must be non-zero. So without loss of generality, we may assume that a of xy not equal to 0 for all xy in D. Okay. Now we have to find two functions. So here we have to find two functions. Theta equal to theta is a function of xy, and eta is equal to eta of xy, such that what are the conditions, or that satisfy the conditions, two functions theta and eta that satisfy the conditions. What are the conditions to be satisfied by theta and eta? Conditions are: when the equation is in the transformed form, the coefficients of W theta theta and W eta eta must be the same. Then only we can divide throughout by the common factor and make the coefficients of both W theta theta and W eta eta to be 1. So first of all, the coefficients of W theta theta and W eta eta must be the same. And the second thing is the coefficient of W theta eta must be 0. Coefficient of this must be 0, isn't it? So coefficient of W theta and W eta are capital A and capital C. So we have to find two functions theta and eta that satisfy the conditions. A of theta eta is equal to C of theta eta, and the coefficient of W theta eta, that is B of theta eta must be 0. So these are the conditions to be satisfied by the two functions theta and eta. So let's write the functions which are what are A and C. And that means that is we have to find theta and eta such that A of theta eta, that is A theta x square plus 2b theta x theta y plus c theta y square equal to C. What is C? C is A eta x square 2b eta x eta y plus C eta y square. And let this be equation number 2. Okay, and B of theta eta, A theta x eta x plus B theta x eta y plus theta y eta x plus C theta y eta y equal to 0. Let this be equation number 3. So we need to find two functions theta and eta such that the system of nonlinear first order equations 2 and 3. 2 and 3 makes a system of nonlinear equations. This equations is satisfied. So actually we have to find a solution for these two system of two non-linear first order equations. So equations 2 and 3. Equations 2 and 3 makes a system of non-linear first system of non-linear first order equations. So the equations 2 and 3 makes a system of non-linear first order non-linear equations. And one more thing you may notice that the two equations are coupled. We can't separate the functions or variables theta x, theta y, eta x, theta y like that. So in order to decouple this equation, we shall use the complex plane and the analyticity assumption. That means we can rewrite this equation. We know that A is equal to C. So equating the taking the coefficients of A, taking the terms containing A into all the terms into the left side and equating to 0, we can rewrite the equation number 2 as A into theta x square minus eta x square like that. So the equations become A into theta x square minus theta x square plus 2b theta x theta y minus eta x eta y plus c into theta y square minus eta y square equal to 0. So in order to use the complex plane, we multiply the second equation. Okay, the second equation is A theta x plus B theta x theta y plus theta y eta x plus C into theta y eta y equal to 0. We multiply this equation with the complex number I. So we will get it as A theta x into I eta x plus B into theta x I eta y plus theta y I eta x plus C into theta y I eta y equal to 0. Okay, so we will change the equation. The system 2 and 3 is changed into equations 4 and 5 with where I is equal to root of minus 1. So in order to solve this equation, we will define a new complex function as phi as theta plus I eta. Okay, now the system 4 and 5 is equivalent to the complex valued equation a phi x square plus 2b phi x phi y plus c phi y square is equal to 0. So when we calculate this equation or when we expand this equation, we can verify that this gives the this is not none other than the two equations 4 and 5. For that we know what is phi. Phi is theta plus I eta sorry not eta x I eta and then phi x what will be phi x? Phi x will be theta x plus I eta x and phi y will be theta y plus I eta y. Then phi x square means theta x plus I eta x whole square, then expand that, then phi y square means theta y plus I eta y square, then phi x phi y, what will be phi x phi y? Some multiplication of two complex conjugates. So that means sorry, not complex conjugates, theta x I eta x into theta y plus I eta y. So it will be theta x theta y minus eta x eta y plus some I into the imaginary part will be there, I into theta x eta y plus eta x theta y like that. So calculating all this, substituting all this in the equation 6, we can verify that this equation is not other than the is equivalent to the system of equations 4 and 5. So verify this. Okay, so A5, the equation, the system is equivalent to the single equation A5x square plus 2b 5x 5y plus c into 5y square equal to 0, where phi is the complex valued function theta plus I eta x. So when we solve this equation 6, we will get phi. The equation phi in terms and is theta is the real part of phi and eta is the real part, imaginary part of phi. So in that way, we can calculate theta and eta. Now look at the equation number 6. And you may notice that this equation is similar to that obtained in the hyperbolic case, the same equation as in the hyperbolic case. So we can factorize first of but the one more thing in this case is that this is not a real function. Phi is actually the complex valued function, and but in the elliptic case, in this case the equation does not admit any real solution. This equation 6 does not admit any real solution. That means the solution of this equation is we called it as characteristics. That means in elliptic case, or in other words, in elliptic case there are no the elliptic equations, elliptic or in elliptic case the equation has no, does not, do not have characteristic. Elliptic equations, we can write it as elliptic equations do not have characteristic. Okay, elliptic equations do not have characteristic means actually the real characteristic do not have characteristics. This is an important observation. Elliptic equations do not have characteristics. But in the case of hyperbolic equation, there are two real characteristics. And in the case of parabolic, there is only one real characteristic. And in the case of elliptic equations, there are no characteristic. But we can solve this equation as in the above it is in the quadratic form, quadratic PDE, and we can solve this as we solved the equation in the hyperbolic case. So first of all, we can factorize this equation 6 as a into 1 by a into a 5x plus b plus I into root of ac minus b square 5y, which is same as in the case of hyperbolic equations. You can verify this with the hyperbolic case that we have already solved in detail. So please refer that video. A into 5x plus b plus I root of, since the equation phi is complex valued function, we are writing b square minus root of b square minus ac as I into root of ac minus b square 5y plus a 5x plus b into b minus I into root of ac minus b square 5y equal to 0. So the equation can be written as and we know we can check that the two are complex conjugates only, so we need to solve the equation a 5x plus b plus or minus I into root of ac minus b square 5y equal to 0. Okay. Since we have already assumed that the functions, the the principal part of the coefficients in the principal part are actually what real analytic functions. These equations, the question of the existence and uniqueness of solutions. Here we can also consider this as the same first order linear equations with that are real analytic. Since the coefficients A, B, C are all real analytic, we can solve this as the same procedure as in the real case. So, moreover, the solution of the two equations will be complex conjugates, isn't it? So, we need to solve only this equation. Let this be equation number. It's the equation number 7. Okay. So now we have to find equation number 7 only. As before, the solutions phi and theta are phi and psi are constant on the characteristics that are defined on the complex plane. That means the characteristics which are defined on the complex plane is of the form dy by dx will be b plus or minus I into root of ac minus b square by a. So these are the characteristics defined on the complex plane, which are done and underestimate with the real characteristics, which are defined on the complex plane actually. Okay, so you can verify that this is the same as in the case of that we obtained in the case of hyperbolic equation. So in the case in the same equations, let this be equation number 8. So as in the same hyperbolic case, in this equation, the transformed equation has the form 4 into v 5 psi plus some function since phi is equal to 0. But this is not in the still in the elliptic canonical form of the real coefficients with the real coefficients. So we return to our real variables which are theta and eta using the linear transformation, and using the linear transformation theta is real part of phi and eta is real part of imaginary part of phi. So using this we can find there must exist two linear transformations theta and eta. So since theta and eta are the solutions of the equations 2 and 3, it follows that the variables theta and eta in the variables theta and eta, the equation has the canonical form. Okay. So the required canonical form is obtained. And one more thing we need to verify that prove that the Jacobian not equal to 0 in the use in the canonical transformation. That means prove that theta and eta the transformation is a non-singular transformation. This also you have to verify. Okay. So let's stop here. The respective problems, related problems we can solve in the next lecture. Thank you. Thank you all.